Oh, it's on. I see a blue light.
Yeah. So welcome Jose Rodriguez from University of Chicago and then University of Wisconsin. He will present on algebraic methods for point estimation.
Great. So thank you for letting me speak to you all today. And yes, the title of the talk is Algebraic Methods for Point Estimation, and I'll be starting at UW-Madison very, very soon. So the outline of the talk, I want to tell you about point estimation, and then I also want to tell you about algebraic statistics, and that will be the approach that we're going to take to attack this problem. Along the way, I want to tell you about maximum likelihood, and in particular, I want to tell you about maximum likelihood degrees, which is ML degree for short. I want to tell you about Euler characteristics, homotopy continuation. Then after this, we'll reboot and get to method of moments and talk about Galois groups. Then after this, if there's, depending on how the talk flows and how much interaction there is, we'll talk about generalized method of moments and how this is related to GMM degree and cost functions. So those are the goals of the talk. And as I said, we'll start with algebraic point estimation. So what is this? So we want to estimate a point in a model given a set of data. So in statistics, point estimation uses sample data to calculate the best estimate. So where best is open to interpretation.
So what's the point in the model?
We'll get there. So let me give you an example first, and then we'll be more concrete in a second. So here's an example. So sample average can be used to estimate population mean. So sample data, you can record the age and years of each person in this room, and then we take the average. So that's the sample average. And the populations may be people that attend this seminar throughout the year. And then we can estimate this population parameter of the average age of age of people that attend the seminar using the sample data. So there are many different. Just told to pause for a second. Hello. Okay, so to recap, we're going to talk about algebraic methods or algebraic statistics for point estimation. And there are many different point estimators, MLE, method of moments, and generalized method of moments. And the first one we'll talk about is the maximum likelihood estimator. And I'll tell you what a model is in this context in the next slide. So, algebraic statistical models. First word that I want to say is probability simplex. So what do I mean by this? So this is going to be the subset of the positive real numbers where all the coordinates sum to 1. So that's this delta n minus 1. The n minus 1 denotes the dimension of this set. Statistical model is just a subset of this probability simplex. Right, so some model M, we could ask what are its model invariants? So what do I mean by a model invariant? So polynomial f is a model invariant of M if for each point in the model, if we evaluate, we get 0. Makes sense?
How should they think about these models? Like, what? Give some simple example.
You'll get a simple example in a couple of slides, but we'll fast forward here to a simple example. So consider a 4-sided die where the probability of observing side I is pi. Right? So then maybe, first model invariant is, the sum of the coordinates minus 1, because all probabilities are going to sum to 1. Another model invariant, we might say, okay, we'll say we want the probability of observing side 1 plus 2 times the probability of observing side 2 plus 3 times the probability of observing side 3 minus 4 times the probability of observing side 4. Say we want this to hold. So this would be some linear constraint. So this...
So describe I, and what was M itself?
M is the model. So this is a subset.
In this example.
In this example, let me write it here. So M. Such that these two polynomials, F1 and F2.
Oh, so that's precisely right.
Like for your description, it sounds like it's like just one point. No, it's
no.
But you have fixed this coordinates.
You have P in.
Okay, yeah. You don't know exact probability, but you just know some constraints on them.
Yes, so it's
and
a set of probability
choose. Okay, I see.
Yes. That's good.
Okay. But isn't it in delta 4 minus 1? Isn't that your second equation?
Yes, that's also my second equation. Other questions? Okay, so that's a simple example. That's fast forward. So now we're gonna go back. So model invariant ideal, because I want to get to algebra. So this is going to be finitely generated. So you can consider all possible polynomials, and by Hilbert's basis theorem, this ideal is finitely generated. So what do I mean by this? That if you had a model invariant, there exists some G1 through Gk, such that you can find H's where you can express the model invariant as this sum. And the G's are model invariants themselves. Okay. So the point is that there may be infinitely many model invariants, but you can always reduce it down to finitely many. And one part of algebraic statistics is finding model invariants for some statistical model which you don't have a description like this for. Maybe it's parameterized. Go ahead.
And also, I suppose that in real applications, M is not always zeroisly closed, right?
That's right. That's right.
So what would you say the connection is about the actual question and what you can find using ideals?
Okay, so let me say 2 sentences and then we'll come back to your question. So this first sentence is just a repeat from the last sentence of the previous slide. So an algebraic variety, we're going to denote by this M bar. So you can think of it as a Zariski closure of the statistical model. And we're going to be considered as a subset in the complex numbers. So M bar is the points in Cn such that for all f in the model invariants, we have at the polynomials evaluate to 0. We say M is an algebraic statistical model if this M bar restricted to the probability simplex is M itself. And here I said I omitted many details regarding closures, and now I'll draw a picture on the board to illustrate some of the issues. Okay, some issues. So,
and would you know in advance or quickly that it's an algebraic statistical model?
That's usually my assumption is that this and where does this assumption comes from? Typically, often, M is given by parameterization. So you have some map. So let's say you have some probability simplices. And so I think of this as I have a red 4-sided die. And then there's some probability of observing each side. And I have a blue 4-sided die where, again, exact same situation. And now the independence model would be the image in this probability simplex. Right? So what I've done is I've mapped this product into this larger dimensional space. And then I could ask, well, what are the polynomials that vanish on this image? And it turns out that, well, if you write this as Pij, then this is a rank 1 matrix. So it'd be all the 2 by 2 minors. That's all minors. Okay. So the question is like, well, how does it relate to in practice? Usually, you're given your model in this form, and in this image, you would know that it's semi-algebraic because you have a semi-algebraic set here, and then the image would be semi-algebraic. And now I took the Zariski closure. So often your model M will be something like this. Some algebraic, you have some curve. And then you take the Zariski closure, and maybe you have something that's like a parabola. And so today, what I would like to tell you about is maximum likelihood estimation. And what I want to do is find critical points on the model M. And I'm going to ignore these boundary conditions because I'm going to consider those as degenerate models. And that would be more of a model selection model. Critical points could lie over here, but the goal is if you find them all, you can then pick your favorite one. And that's the way.
And are there any related issues in regards to going between complex and real numbers?
Yes. So let's see. So with complex and real numbers, you could have. So usually the Zariski closure is nice because if you have a d-dimensional real set, take the Zariski closure, you'll get a d-dimensional complex variety. So that's not such a big issue, but with these closures here, this will be a big issue, but I'm going to gloss over that. Let's see, what else do I want to say? If you want to solve it using symbolic computation, then well, good luck extracting the real versus complex, but we'll use numerical methods to filter out the complex critical points and real critical points, and that's how we'll overcome that issue. Right? So let's see where we're at now. So let me tell you about the likelihood function, which will probably be all we get to talk about in today's talk. That is okay. So the likelihood function with respect to some data U is this monomial here. So how you should think about it is that U1 is the number of times you observe event 1, U2 would be the number of times you observe U2, and so on. The gradient of the log likelihood function is nice. Why is it nice? Because it's a rational function in the U's and the P's, in the data and the probabilities. The likelihood equations, you can think of these as KKT conditions, define critical points of the likelihood function on our variety, where M is an algebraic statistical model. If M is an algebraic statistical model and U is generic, then the maximum likelihood degree of M is defined to be the number of critical points of this function on the model. Go ahead.
So when you take gradient with respect to P's or U's?
P's.
P's, okay.
Yes, gradient with respect to P's. Are used, you should think of these as being, you can think of them as being fixed. You want to solve it for this particular choice.
So the data, like, where shouldn't be known?
Yes.
Okay.
Yes, the data is known and you want to find the P's. Right?
Okay.
I want to be a little bit careful. So here I'm going to assume that critical points are in the set of smooth points of my algebraic variety, and they have no non-zero coordinates. Why do I want no non-zero coordinates? Because if I have a zero coordinate, then the likelihood function vanishes, and well, it's zero, and it's not going to be a maximum. And if it's in the singular locus, then you should be considering a different problem. You should focus on the singular locus separately. And we've defined the ML degree for an algebraic statistical model, but how we defined it was by passing through a variety. So you might as well define an ML degree for an algebraic variety, and that's what we'll do today, or that's what we've done today.
And draw picture refers to...
Draw a picture. How about I give you a simple example again?
No, it was a reminder for you to draw a picture.
Oh, where is it? I already drew this picture. This is the picture I wanted to draw. Yeah. See, I have reminders in the top because otherwise I forget. Thank you. Other pictures you'll want to see. Let's see. Okay, so consider again our four-sided die. And say we roll this four-sided die 100 times. Then we observe this data vector, 10, 22, 28, 40. So what does 40 mean? 40 is the number of times you observe a 4 when we roll the four-sided dice. Right? The likelihood function is this monomial here. And the maximum likelihood estimate maximizes this monomial over our model. And it's going to be one of the three critical points found by solving the likelihood equations. So here are the 1, 2, 3 critical points. And here's the one that's the winner, but the maximum likelihood degree is 3 because we had 3 in the generic case.
Could you read the definition of maximum likelihood degree?
Yes.
It is just.
So if M is an algebraic statistical model and use generic,
That's just number of critical points. Okay.
yeah,
Okay,
just number of
good.
critical points. Where a little detail about what I mean by critical points. Excuse me. So if you wanted to, you could derive closed form expressions for the maximum likelihood estimate. So here is a tiny polynomial, or big polynomial in tiny font. Or not. Here's a polynomial in tiny font, and it's a polynomial that's univariate in the P1. So, this is probability of observing event 1, and then the coefficients are in the data U's. So here's a closed form expression. If I were to plug in U's, I would have a degree 3 polynomial whose roots would be 1, this one, and that one for that choice of data.
So by the way, you're doing this because some prime methods, existing methods, they're not good, or could you explain?
Why do we want to do this? Good question. So let's draw another picture. Say this is my statistical model for my drawing skills aren't so good. And let's say we have 1, 2, 3, 4 critical points. And now what we want to do is and so here's our model, and here's our likelihood function. So it eats a point in the model and spits out a number. So let's say we started here, and now we want to find the point in this model that maximizes this function. So now we could use some local methods, so where we move around a bit and always making this likelihood function increase. But what could happen is that, say we keep going up, and here is a local max, then we're stuck. And so you would have to restart your local method somewhere else, and maybe you converge to some different critical point. So that's the point of this method, is that you find all the critical points, and so you're able to find the global maximum and not just the local maximum.
What's the definition of critical point again?
Let's see. So critical point. One more. So point P in the algebraic variety is a critical point if this Jacobian matrix augmented with the gradient of the likelihood function is ranked efficient at the point P. But we also want the condition that P is not in the singular locus of our algebraic variety, and we want P not to be in the coordinate hyperplanes.
Like the reason you consider this definition is that this is like local extremums, right? Local extrema of the.
That's right.
Okay.
That's right. Because we came from.
And to clarify, so you would like to find something called maximum likelihood estimation. right?
That's right.
That's your goal.
That's right.
And you define some ingredient to find called the likelihood function.
That's
right.
right.
Now, for the original question, maximum likelihood estimation, this like the prior history of.
The maximum likelihood estimate
Mm-hmm.
is the Argmax of the likelihood function on the model. Does that answer your question? Or?
And so, was this considered in statistics itself?
Yes. So, yes, it's a fundamental optimization problem in statistics.
And are there solutions for that problem? How do they relate to
So one solution is for these local methods. So you do an EM algorithm for a class of problems. There's a notion called the EM algorithm. And so you start at some point in the model, and then you work your way up by increasing the likelihood function. But it is well known that this has a problem that you can't certify that you found the global maximum. You can only certify that you found a local optimum. And so the idea of these methods is that, well, maybe you're going to pay a huge price to find all the critical points, but why do you find all the critical points? Because this will include all the local maxima. So if your maximum likelihood estimator is a local maximum, then you would have found it and solved the maximum likelihood estimation problem. Whereas other methods, you could restart your local method many, many, many millions of times, but you would have no provable guarantee that you actually solved the problem. So that's the difference between the two.
Okay, thank you.
Yeah, other questions? Yeah. Okay. So some background for the maximum likelihood degree. This was introduced in some papers, two papers, solving likelihood equations and the maximum likelihood degree. The one on the top in FOCM, this one gives you equations to solve this, but it was more of a symbolic approach. These ML degrees, or maximum likelihood degrees, in some cases are related to Gaussian degrees and weighted Euler characteristics. And there's some study here, which I've also been involved with. And there's been many applications in statistics. So there's Caroline studied Gaussian graphical models, and then Elizabeth, Matthias, and Sonia studied different class of models. So this is well studied, but today I focused on discrete models, where we're in this context that I gave earlier today.
But why is it important to know ML degree?
I'll get to that in a second.
Mm-hmm. And star is for you?
Star is for me. Yeah.
Okay, that's okay. Yeah. So I didn't see your name.
Yeah. Well, different. Yeah. Okay. I won't say anything. Okay. Euler characteristics, ML degree. So I wanted to do two things in this talk. One, to give you some topological approaches to determine what the ML degree is of a statistical model. And then after I did this, I was going to tell you how knowing the ML degree can help, given some other computational methods. So let me tell you about these Euler characteristics in ML degree. So if X was a smooth, irreducible variety, then if you consider XO an open variety where you rip out the coordinate hyperplanes, then Ha proved that the ML degree of a smooth variety X equals the signed Euler characteristic of this open variety. So in other words, -1 to the dimension times an Euler characteristic is the ML degree. So you related the topology of a variety to the number of critical points of this function that comes from statistics. So let's talk about the independence model, which I already gave you a preview on the blackboard. So this independence model will denote by MN1, and it's a subset of this probability simplex here. And as we saw on the blackboard a little while ago, we had this m-dimensional vector and an n-dimensional vector, and we took their outer product, and we got this rank 1 matrix. And this is this image here. This is the independence model. And you can think of it as rolling a red die and rolling a blue die, where m is the number of sides on the red die, and n is the number of sides on the red die. Or flip that. So if X is the closure of the model, then what you can do is you can get a parameterization of XO, and which comes from by considering this open set here, where sum of the coordinates equal to 1 with the hyperplanes removed. And using inclusion, exclusion, and additive properties of Euler characteristics, you can determine that this Euler characteristic is equal to -1. If you want to exercise for some topology students, show it for the m and n equal to 2 case. But the important thing is the step at the end where this map here is a homeomorphism, so the Euler characteristics are the same. So they're both ML degree 1. Now, why is that important to know about a statistical model? Because if you know that ML degree is 1, then you can express the maximum likelihood estimate in a closed form way of the data. There's just one critical point, and so it's easy to find it. If you had some local method, as we discussed earlier, it's always going to find this one critical point. However, what's more interesting are mixtures of independence models. And these are much more complicated because there's a hidden random variable. So here's the independence model. The two-mixture independence model you can think of as a sum of two rank 1 matrices. So this is a rank 2 matrix, rank at most 2 matrix. But these models are singular, and H's result no longer applies. So you'd want to know what are the ML degrees of this. And so you would ask, well, is the ML degree 1, or how large is it? Is the question clear? Let's see. So what we did is we used some tools in algebraic topology to show that the ML degree of this two-mixture case is given by this formula here for some choice of lambda 1s and for some choice of lambdas. And so we give a recursive way to actually compute these numbers. Okay. No. Okay, so these are, so you might ask, well, what is this first row of numbers? And so we conjectured that it was 2 to the n plus 1 minus 6. So let's check if, the second row. So you should think it as 3 by n matrices. So then it was 2 to the n plus 1 minus 6, and we were able to prove this result. And so, but unfortunately, there's no closed form expressions, so this motivated the numerical methods. So, as you see, the numbers get very big, which is a bit unfortunate, that but it also shows that the problem is really hard. There could be potentially many local maximum, and you have to be careful if you conclude that you've actually found the solution. So to recap, ML degrees give an algebraic notion to complexity of MLE, computed using topology, combinatorics, and other algebraic geometry methods. Critical points can be computed directly using parameter homotopies and local to global methods. And this is the part where the ML degree will be related, and I'll discuss on the next slides. Okay, questions so far? What is it happening? So.
So you have all these critical points.
That's right.
One of them is the maximum.
That's right.
Maximum in what sense again?
It maximizes the likelihood function.
The likelihood function. That's a unique one?
Yes, it'll be unique if the data are generic.
But you cannot have different generic data giving you different maximas. All the generic data will all give you the same maxima?
No. So
they can give different maxima.
Yes. That's right. That's right. So
in your example, the four-sided die.
Yes.
And you give us concrete example. Do you have the maximum likelihood example there? What is in that case? This one.
For that choice of data. if you were to change that data, this value would change.
Right. So how do you read that data now? You said the probability of observing 1 is 0.102 and so on.
That's right. So these should add up to 1.
Really?
After location.
Can one look back at the original data and say that this makes sense? The original data is 10, 22, and so on.
Yeah,
So roughly,
10,
roughly.
If you divide everything by 100,
Right.
10, 20, or if you multiply this by 100, 10,
Right,
23,
roughly
30,
1, 2,
36.
2, 4, something like that.
Yeah.
1, 2, 3, 4. Right. Okay.
Yeah.
Sure.
What can happen is if you choose your U's to be special, then these 2 points, or sorry, some of the critical points could come together.
Mhm.
And that's for studying the data discriminants of these things. So you could ask, well, for which set of U do you have exhibit these special behavior? But that's a different talk.
Mhm. Sure.
Other questions? So, there's some system of polynomial equations which are used to describe these critical points. So we'll denote this system of polynomials as f p equal to 0. And so now you want to solve this system of polynomial equations. And maybe one way you could try to solve it is using some type of homotopy continuation software like Bertini, PHCPAT, or use Grosvenor basis to get some idea of the degrees. But this can be quite daunting and quite computationally expensive. So what's a different way that you could solve the problem? And a different way you can solve the problem is, say you're given one solution. Say Z, say fix U.
So in your example here, what are your equations in this case?
In this example, so that's F1, that's F2. Then we have the gradient of this. But this has p's in the denominator, so now you need to multiply this. Like that. And then now you hit this with you have this here. You hit it with Lagrange multipliers. So now you want this to be equal to 0, as well as have those 2 equations vanish. Now, in this setup, because you clear the denominators, the resulting equations will look something like these equations look like g of p of lambda equal to u. So what you can do now is, let's say you had one solution to this system of equations. We'll call it z for a particular set of data u. And now from this one solution, I want to discover new solutions using a method called Monodomain homotopes. I don't know. Are anyone aware of Monodomain homotopes or Galois groups? If not, I'll say some stuff about this because that's the technique that I want to describe.
How do we get one root? This is like
So one is easy. It's easy to find one solution. Why? So take a choice of p, you plug it in, and now this gives you u for free. Right? So if you had a point in the model, you take that model, you plug it into these equations.
You should just take 1 over, your data u, right?
That wouldn't live in the model.
What's that?
That wouldn't satisfy F1 and F2.
Right.
So, if
P
you,
has to satisfy.
so you take a point in the model,
Mhm.
you plug it in here,
Mhm.
then you take that to be the u. So now you have a pair.
I mean, I don't need U be the same as my U from actual experiment.
That's right.
So there's different U in the last row and in the first row.
So it's easy to find this, and then you could do it, do a homotopy that deforms
U also.
that U, and then you have it for free. So that's
Okay.
super easy, right? Idea clear?
Yeah.
Okay, so we all believe that it's easy to find one solution. We all believe that it's hard to find all the rest at the moment, so far, potentially. But, okay, so, yeah, we're skipping all over the place, so. So I have 15 minutes. Let me think how to best present this material. So what I want to do is I want to start with a simple example. And then from that simple example, I will relate it back to what we've been talking about today. Right? So our simple example is x to the fourth minus 4x squared plus t plus 3. So now this defines a variety in a product space, CT cross CX. And what I want to do is I want to let gamma denote a simple loop in T space. And I want this loop to start at t is equal to 0 and not pass through the points minus 3 or 1. And what this loop does, it induces a permutation on the fiber over 0, where this pi is a projection to T space. So let's do a demonstration and draw a picture. Good student should label your axis. So here's t-axis. Here's x-axis, yeah? So this polynomial f defines this algebraic curve. Here, at t is equal to 0, we have 1, 2, 3, 4 solutions. So this is analogous to our data. For our data, we had some number of solutions. And now, I want to consider a loop downstairs in t-space. So what does this loop do? It'll induce a permutation on these 4 solutions. So how does this work? So here we go. You'll have to bear with me a little bit. The room is not, yeah. So here's our axis here. Can lie it down. Now over t is equal to 0, we have our 1, 2, 3, 4 points. These are x coordinates, yeah? So let t is equal to 0. Were they listed? Okay, I don't know what happened to my x coordinates, but we lost them. There are 4 coordinates here. There's a picture, right? And now, if you take a loop downstairs, then what happens? Then these 4 points will start to move around.
What do you mean by loop downstairs?
Good question. So here's a space of complex numbers right here on my table, or on your table. And here's this real axis. At t is equal to 0, we're here, and we have our 4 points in the x coordinates of complex numbers. Now, if we were to take a loop, so that means just take a real one-dimensional space that comes back to itself at the origin. Now what happens? Now down here, this at t is equal to 0, now we have some complex number close to 0. And these will be moved around. And then as we move around downstairs, then this causes these solutions to move around. And what happens when we come back to 0, then they come back to each other. But they could have been permuted. Make sense? So here, again, here's our real axis. Here's our real axis. Now here's our complex numbers. It's a 2-dimensional real space. We can move around in it and take a loop. We take a loop, and then these 4 points will go like this and like this if we went around like this. Why? Because right here is a special point. So here's t is equal to 0. That way we mark it. This point here is a branch point. We see that these 4 points will come together. So if we went along this line, we would have these things coming together. And we don't want that to happen because that's the discriminant locus and our methods would die, or numerical methods would fail. But if we went around like this, then what happens? These swap and these swap. Okay? Now, why is this useful? Well, it's useful. Let's focus on the orange guy. So this solution we say is known. And if we were to come around, then this orange guy will go to one of the other solutions. Now, if we were to go around this other branch point here, then this orange guy will jump down here. So now what we've done is by taking these two loops, we found now a total of 3 solutions. We go around again and then hope to find the 4th. Make sense? So from one solution, using these Monodomain techniques, you're able to find others. Now back to your question. Well, maybe I'm going to read your mind and say what your question is. Your question is, well, how do you know you found them all? Right? So here I'm assuming I knew I had 4 solutions, but if I did this method maybe 10,000 times, how do I know I found all the solutions and I just didn't find 4? But now that comes back to our problem of maximum likelihood degree. If we knew what the maximum likelihood degree was, this would give us a stopping criteria for when we found all the solutions. Okay. How does this Monodomain method compare to directly solving systems? Go ahead.
Still, because you changed coordinates, right? So in this example, you have t and x. So which of them will be u and which of them will be p when you will be working in your setup?
Perfect question, and I knew you were going to ask it. So then here's an example to illustrate it. So the subtitle. Let's relate this part of the talk to the previous part. So here, our model invariants is this determinant. It's a degree 3 polynomial, and the sum of the coordinates being equal to 1. So this is this defines an algebraic variety in complex 9-dimensional space. But the likelihood equations also define a 9-dimensional variety in this product space. The maximum likelihood degree is 10 for this model. And the degree of the fiber is 10. So what is this saying? The likelihood equations, here, the analogy, this would be P, and this would be U. And now instead of a one-dimensional space, a one-dimensional complex space, now you have a 9-dimensional complex space. And then instead of just having 4 points, you have 10 points in this example, or ML degree many points in the fiber. Make sense? Okay. So we did some other things that say that, okay, that this could ask what are all different possible permutations that could occur, but I'm not going to tell you about that. The point is that you have this analogy here for the likelihood equations. And what happens whenever you take this approach? Well, previous work, we used PHC and Bertini to directly solve the likelihood equations, and they took some amount of time. But if instead you did this local approach, where you did this collection of solutions, we were able to knock down these times significantly. We made a vast improvement compared to the previous times. And so these local approaches, local to global approaches, they're very good for when the ML degree or ED degree is very small, and ED degree is something different.
Who invented this Monodomain?
So this was our implementation.
Okay.
There are other, so we did this for critical points, for the Euclidean distance degree function and the maximum likelihood, the likelihood function. Recently, there's been work to implement this in Macaulay 2, and Tom Lincoln, and that group has a package. And let's see. And already there are some other Monodomain techniques to compute the degree of an algebraic variety. Other questions? Okay, so how much time do I have? Am I out or?
7 minutes.
7 minutes. Okay. So that was maximum likelihood estimation, and that was like the first part of the talk of 3. And so you'll have the first part of the talk, and here's part of the second. And it involves method of moments. So consider the standard normal distribution. So the standard normal distribution, it depends on the mean and the variance. So those are your statistics parameters. And the method of moments says, all right, here's somebody from data, you extract M1 and M2, and now you solve for mu and sigma squared. So given the sample moments, this determines the parameters, mu and sigma squared. The point is that this is a polynomial system, and this has been studied by Carlos, Bernd, and Fougère. Now, what's more interesting is mixtures of mixture models. And so the mixture of 2 Gaussians, you now need more moments to identify the parameters because there are more parameters. So here, again, though, it's a system of polynomial equations. And this system of polynomial equations has 18 solutions. But this 18 is really 2 times 9. And why is it 2 times 9? Because you can label swap. And so the Galois group, which is these possible permutations that can occur, is structured. And so we exploit this structure to determine what these solutions are. And so we use this in solving systems of polynomial equations with decomposable projections. So this is one example that came up in statistics. We have others in kinematics, and I don't remember the third one. Maybe it was computational algebraic geometry. So since I'm running out of time, I just want to say that Galois groups appear in applications. Knowing the ML degree allows you to use the Monodomain method to solve the likelihood equations. And knowing the ML degree gives you some idea of how complicated the model can be. My belief is that if the Galois group of a problem, which again is this possible permutations that can occur, if it's not the full symmetric group, then this should be explained. And so examples where this phenomenon occurs is kinematics, tensor decomposition, algebraic statistics, and formation shape control. And then we explain this idea, and I try to explain some of these to you about the algebraic statistics problem. GMM, I won't talk about at the moment, and instead, thank you, and here's some advertisements for things that are coming up in the applied algebra and geometry community in Bern, Switzerland, and there's an ICERM going on this semester. So I'll stop on time. Thank you for your attention.
Thank you.
What is your kinematics example?
Let me think. It was this four-bar mechanism. And then, so there's the explanation was you have Roberts coordinates. So you can like flip this.
So it's a loop? Is it a closed loop?
Closed loop. Yeah. And so you see how this coupler curve moves on.
How many degrees of freedom?
This I couldn't tell you off the top of my head. I'd have to remember.
Planar, right?
Yeah, it's
planar mechanism. So 4 bars is, one point is fixed.
1 point is fixed.
So 1, 2, 3,
4. But you also have the
rotation.
Yeah,
4, I guess.
Don't call me on that, but
Yeah, like if you fix 2 bars, right, then
Right.
2 others are fixed.
Right.
So it's like 2 degrees. Okay.
yeah.
3 or 4. Okay.
Yeah, I'm horrible with dimension counts on the fly. I always have to write everything down.
And the goal is to find what?
The goal is to find, say you want the mechanism to pass through a certain number of points. How are the different ways that you can construct, how many different ways can you construct it so that it goes through these different points?
With fixed parameters for the lengths.
No,
The length is all determined already.
No. So you're allowed to make the lengths as you wish. What's fixed is you want the mechanism, you have some coupler triangle, and you want it to pass through this point, and this point, or these 2 points. And so now, how many different ways can you construct the mechanism so it does this? Now, for the, where am I? Yeah.
And what methods do you usually use to find the Galois group? If you have like a system, what are
I don't think so. We have a method called the branch point method. So it can be summarized by this picture here. So here we have some polynomial f. And we want it to be equal to 0. And so now you want to find the critical points. So you take the derivative of f to be equal to 0. And then now you find the t-coordinates where this occurs. And so this, you'll find this point and this point. And so what you do is you take, so here you
just take 2 permutations, right, and generate a group by them.
That's right. So you start from here, you take your loop around, whoop, here, and likewise over here, whoop, there, and come back. And so here you would think, okay, sorry, is that okay?
Yeah.
Okay, so we did this in some examples, and then what was remarkable is that you're actually able to do it. So you might think that, so originally I gave a talk about our idea I think it was in Korea, and Frank's like, there's no way that this is going to work because there's going to be too many branch points. But it turns out that in these kinematics and algebraic statistics problems that the number of branch points is not so big. And so you can actually find all the branch points.
Number?
You'd expect it to be on the order of d squared, because here is the degree d polynomial, here's d minus 1, d squared, but it was much smaller than this. I couldn't tell you what the numbers were.
T is the complex parameter.
T is a complex,
One
dimensional. So here, what was one of our ideas is that here we had this use space. Our data space is 9-dimensional. So what you do is instead of working with this 9-dimensional space, you restrict yourself to a 1-dimensional family, or 1-dimensional space, generic 1-dimensional space inside of here. And this Galois group is now a Galois group of the projection of a curve, rather than this 9-dimensional space. These are the same, and we have algorithms that implement this, that actually do this. And so that's how we did our computations.
And where do you implement your algorithms?
So our implementation was in College.
Okay.
Yeah.
More questions? Could you say a little more about the ads at the end, so about the conferences?
Yeah. So let's see. So I can't tell you the date of the Bern Switzerland one, but I'm a mini symposium organizer for algebraic statistics, so I'll have a session. I think we already have 6 confirmed speakers. That's exciting. I think Thomas Kahl is one of them. He'll be speaking here with y'all. And I'm also an organizer of the numerical methods in algebraic geometry with Paul Brading. And this one I just found out about yesterday. And I'll be there in October, but I can't tell you much about it because I just found out about it and they don't have a website up yet. But it's, I believe, my understanding, it's to promote diversity and for underrepresented groups in mathematics. This one here is going on right now. So I'll be here at the Core and Computational Methods week-long program at ICERN. So that's in Rhode Island. And I'll also be back in November for the nonlinear algebra and applications. In between that, in October, there's a week in real algebraic geometry. But I have to teach and I can't come to everything. So these are some of the things that are coming up.
And you suggested to attend the workshops?
Yeah. I suggest if you
Be
want
aware
to,
of it.
yes, be aware of it. Come if you want to come. I can't pay you to come. I don't have that kind of funding at the moment. But yes, I think everybody's encouraged and to be aware of it. And also, I might be getting a new email, which I'm very excited about. It's just my name. I used to be Joe. It's the first three letters, or first two letters of each of my names, Joe Israel. But then that was a bad choice because the I looks like an L. So new email will be Jose. But that's what they told me it will be. But yeah, so there's a lot going on.
Thank you.
Yep.